Okay, we're back for the fourth tutorial, this time about LSTMs, long short-term memory networks. In the previous video we have discussed a little bit about the theory of LSTMs, and now we will have a look in PyTorch how to use LSTMs in PyTorch. I will try to keep this video shorter because the videos, again, they're much longer than I planned to do them, or longer than I planned them to be. So yeah, please read the descriptions in detail, and I don't have to go over every detail again, which is already in the description. So please read the first part of this introduction, so how to create an LSTM. So the basic thing for the LSTM is to instantiate the NN, a neural network.lstm object, and as parameters you have the input dimension, so how large is the input vector. If it's a word embedding input, so how many dimensions does the word embedding have? And the second parameter is the size of the hidden state, which is used inside the LSTM, and can also be used to produce the output. Then here as the second line, we just create some random sequence of numbers. Actually we create 5 of them, which is here. Then we create a random hidden state. So this is just to test or to show how to feed some data into an LSTM. Then one way to feed data into an LSTM is to iterate over the inputs. So we have created some inputs. This might be 5 words and their embeddings, or some kind of sequential input. So we can iterate over the input, feed the input to the LSTM together with the hidden state, the initial hidden state, and we get a new hidden state and an output state. The output state is actually just a collection or the sum of all, not the sum, it's a list of all hidden states which have been previously calculated. So you can iterate over the words in this way and update the hidden state of the LSTM until you are done and you have the final hidden state, which you can then use, for example, for classification of the document. Or you can use the intermediate hidden states to create some output, like a part of speech tag for the input word. The second way how you can feed inputs into an LSTM is to just feed the whole input at once, which is done in this code block down here. So we just concatenate all the inputs into one input tensor, which now has this 5 inputs inside this one tensor. And we can feed this one into the LSTM just at once, and it will do the same operations like if we feed it in this loop which you have seen above. So those are the 2 ways to feed an input into the LSTM. Either loop over the single elements or feed the input at once. Yes, okay, then next let's have a look at an example on how to use an LSTM for part of speech tagging with PyTorch. Again, please read the description about what we're doing, but let us here just look at the code. So we have first a function to just convert the input sequence into a tensor, which we can feed to PyTorch. Then we define some very, very small training set of 2 examples where we basically have sentences and they're part of speech tags. In the next step down here, we just create the dictionary to map words to indices. So that's all in here. And we also have a dictionary which maps the tags, the part of speech tags. So we have here only 3 part of speech tags, which we use, which are determiner, like an article, for example, noun and verb, and we map them to some integer values. And then we define the size of the hidden, of the embedding dimension, and of the hidden dimension with very low numbers. Usually this would be much larger numbers in a production setting. Okay, so now we have set up these basic functions, these helper functions. Now we can define the LSTM object itself. As always, we have an init and a forward function. In the init function, firstly we define our embedding layer. So we have first an embedding layer. Input is vocab size, so the parameters are the size of the vocabulary and the size of our embedding vectors themselves. Same as last time when we discussed embeddings. Now new is this LSTM layer. The input size of the LSTM layer is the output of the embeddings layer, and is the output of the embeddings layer, which is the same as to say the size of the vectors for a single word. In an LSTM we feed the sequences, the words, like sequentially, so we only need as input one single word per time step. So the input size is the size of one word, the embedding dimensions. And then we also have to define the hidden dimensions for the LSTM. And then finally, to create an output from the LSTM states, from the hidden states of the LSTM, we use a linear layer. So we use some linear transformation, some affine map, to map the hidden vector to an output vector, which has input size, hidden dimensions, and output size, the tag set size. We have in our case 3 tags which we have defined, so it will be output size is 3, so it's like a classification of a word into those 3 possible classes. Next is the forward function. As input it gets a sentence, which we want to part of speech tag, and here then we define the computation graph. So we feed the sentence into the word embeddings, so we basically transform it into word embeddings. Then the embeddings which are generated for the sentence, we feed them into the LSTM. Then we get some LSTM output for this sentence. Then we can take this LSTM output and feed it into the hidden to tag linear layer. So the LSTM out, it's now all the hidden states for the words. So if you remember the first argument, which is returned by the LSTM model or the LSTM object, is the list of all the hidden states which have been produced. So if it's a 5-word sentence, then here we have 5 hidden, the 5 hidden states in the LSTM out. So and then we can use the linear layer to calculate for each of these hidden states the output state, which is the tag which we want to predict, the part of speech tag. This is then called tag space, and on this tag space we, like always, mostly in the most times so far, we apply a softmax function to convert this into probabilities for the different tags, and this will return. Okay, then finally we can train a model. So we instantiate the LSTM tagger, we define a loss function again, define the optimizer. It's the same like with word embeddings, loss the sim loss functions and optimizers I think that we're using. I think the learning rate is, in this case, they set it higher than last time. Then as a first step, here the author of this tutorial, he just wants to print the outputs which will be generated before training the network. So we feed the inputs to the model, and we get the outputs before training. So this should be random results which we generate here. But he did it to see afterwards that after training we have some very different results than before training. Then in the second step, the main step here is to train the model. We do it for 300 epochs, which because we have so little training data, we run more epochs than it would usually be done. We iterate over the sentences, the training data, and the labels which the training data has. Zero the gradients. Then we just create... Okay, there was a little hang in my video. I hope it will be fine. So the second step is to create the encodings for the so the tensors for the sentence and for the targets. For the sentence and for the target labels. We feed the sentences into the model. We get some scores for the sentences. Create the loss for those predicted tags. Call backpropagation to compute the gradients, and then optimize the network in the last step, and this way iterate over the training examples. After training is finished, we can now see the difference in the predicted values which we just print in this last block. Okay, let's look at the output. This first tensor are the predicted part of speech tags before training, and as you can see, the numbers are mostly on the same order, so it's mostly just randomly or evenly distributed. And after training, we can see that for the first word, I think this is the word the first tag, part of speech tag, hits by far the largest number, so because it's negative, so it's the largest number. For the second word, the second part of speech tag is the largest number. For the third word, the third part of speech tag is the largest, and for the fourth word, the first part of speech tag again. So we can have a look into the data if this makes sense. The input sentence was the dog ate the apple, and as I remember, the first part of speech tag is a determiner, so an article, so the first and the fourth word should be articles, which we have correctly predicted. And then the second word is dog, and the second part of speech tag is noun, so which is also correct. Second word and the fifth word are nouns, and so on. So now the predictions are very good, which have been created by this LSTM model.